Thank you. Thanks, Pucci. Thank you all for coming. And you find that this is a very long title, but actually it's very easy, a very simple approach just to identify types of 3D solid objects in a digital model. So first, a little bit of myself. My name is Ling Ma. I received my PhD in Huazhong University of Science and Technology, and then I started as a postdoc and worked at Technion for 3 years. During that time, I also did a secondment to US at Georgia Tech for half a year. And then, since this year, I started working at University of Huddersfield in the UK, and first as a research assistant, and then I was appointed a lectureship. Okay, so Huddersfield, for those who haven't been to Huddersfield, it's the 11th largest town in UK, and it's halfway between Leeds and Manchester. It's just about half an hour, 20 minutes drive to Leeds, and it's not far from Sheffield, so it's worth visiting. And our university, University of Huddersfield, is relatively new in the area of digital construction and built environment, but our staff has accumulated some research records in related areas. For example, we have developed a spatial temporal safety early warning system for underground construction using machine learning, and we have developed a system for that can automatically generate beam model of earthquake damaged buildings. And we have developed agent-based simulation to simulate the construction workflow. And also we developed a beam protocol which defines a series of beam-enabled technologies for housing retrofit planning. And also recently we have developed a series of VR, AR, mixed reality applications. For example, we use VR to visualize construction simulation in the virtual environment. And also we use terrestrial laser scanning photogrammetry to document the as-is state of facilities. For example, this is our CAD room. And then we visualize it in the virtual reality for the purpose of facility management. And also we did some mixed reality experiments. These are videos just shot next to my house to visualize, to review the design holographically right in front of you in 1:1 scale. And of course, you can also interact with the model. Like many of our colleagues, including you, we are doing beam-related research. So beam has been talked about for decades. What makes beam different from 3D CAD? We say that it's not only geometry. The benefits gained from building information modeling correspond to the quality and the depth of the information in the model. So we say that, that's why we also say BIM stands for Better Information Management. So that's the case. And also, object classification is a fundamental piece of information in the model. Obviously, if you want to prepare a BIM model, first thing you want to decide what type of object you want to add into the model. Is it a beam? Is it a girder? Is it a slab? Etc., etc. And then you define the dimension, define the properties specifically for this type of object. So object classification is a fundamental piece. And then, when could the object classification get wrong? First, you may model it inappropriately. For example, the designer intended to model this precast joint filler street. And of course, there's no such kind of thing in the object library of any BIM software. So the designer, he has to use some objects which has similar shape. For example, in this case, a vertical longitudinal object, a column to represent this object. Then things get wrong. If this guy hands this model to others to transform, to exchange the model, then you get a model with an additional column, which makes things not correct. And also yesterday, we had some nice presentation from Maz and Aaron talking about the ontology things. Also different domains, they have different naming conventions. People name it differently for the same thing. For example, you may see this is just a precast plank or hollow core slab. So they name it differently. They name it based on their own domain knowledge. Also, because those software interoperability problems exist for a long time, and that when you exchange the model, when you share the model, when you transform the model, things also get wrong. This is a model that is built in Revit. Then when you upload to A360, you can see, okay, from the property, you can see, oh, this is the roof, this is the wall. But the property of this window cannot show you this is a window. When you exchange the model based on the property, you cannot infer this is a window anymore. Things even get worse. The Revit and the A360, they all come from Autodesk, the same company. But this model is built in ArchiCAD. When you upload it to A360, the object types just completely gone. So there's no this kind of semantic information exists in the model anymore. Also, there are other scenarios we need to supplement this object classification information. For example, this is a project that we did when I was working at Titanium with Raphael. That this is a transnational research project. We use terrestrial laser scanning, mobile laser scanning, photogrammetry to collect the point cloud data of 18 bridges across the world in US, Haifa, Israel, and Cambridge, UK. We reconstruct a 3D model using this point cloud data from the point cloud data. Then, as we said, a BIM model is not just a 3D CAD. You need the object. You need to identify this type of object. Is it a beam? Is it a girder? If this is a column abutment, at least you need to supplement this information. Let me show you how we did it. It's very easy. First, you list all the object types you want to identify in each row. And then you list all the features that a domain expert, for example, in this case a bridge engineer, may use to recognize this type of objects. For example, longitudinal, transverse, vertical, etc., etc. And then you ask this bridge engineer just to fill in this number. 1 signifies yes, this object type always has this feature. -1 means never had. So in this case, you can explain this. Primary girder is always, for this specific type of bridge, primary girder is always longitudinal element. It's never in the transverse direction of the bridge. It's not vertical. It's not convex. You know, this I-shaped arched girder have a concave cross section, and transverse beam, etc., have similar thing. And then when you get a 3D CAD model without any object classification information, we developed a series of algorithms that can automatically extract these features of each object, each unknown object, pure 3D, solid. And you extract the value the same way that you have this matrix. And then you can see that in this matrix, each row is a vector, what we call feature vector. So primary girder has this 4-dimensional feature vector, 1 minus 1 minus 1 minus 1. And then this object, each of these objects also has a feature vector. Here is -1, 1, minus 1, 1. And then the similarity between these two vectors represent how similar they are. The angle between these two vectors signifies how similar they are. So you just calculate the inner product. In this case, object 1, the dot product of object 1, the primary girder is minus something. So the angle is 180 degrees. So they are completely different. And the angle is 0 degrees, so, which means they're quite similar, almost the same. So you say object 1, in this case, based on this feature matching, is that object 1 is a transverse beam, and object 2 is a primary girder, and object 3 is more likely to be primary girder than the transverse beam because the angle is smaller, right? And this is an example that we have 8 types of bridge objects that we want to identify. And then they have 4 features that we use for the object identification. And then we have a synthetic bridge model. We have an engineer who prepared this bridge model using Tekla. So in this bridge model, we have about 59 objects, and then for each object, we extract the features, have this feature matrix. and then you just calculate the value in the product. So first object has this similarity value within each of these types. One means they're very close, they're almost the same. So then you just sort the candidates. So first object is more likely to be a column and share key than others. As you see, the similarity value, a lot of similarity value is the same, which means that they cannot be distinguished because we have very limited features to identify these objects. Some features for different objects are same. So singular feature has some limitations. We have to add more and more features in order to distinguish different type of objects. Then we try to figure out, is there any other way to help us to identify 3D objects? So we developed a cloud-based system. We upload the BIM model. We developed a series of operators can calculate the pairwise relationship. So you choose one object, you choose one pairwise relationship. For example, in this case, a contact. Then you can select all the objects. You can only select only the object that is in contact with this girder, this piece of girder. Then we do some more. We explore the model with more and more pairwise features. For example, you select this object, and then you choose the objects that are below it, have lower and bottom face, and are shorter than the object, and are smaller than this. So progressively, you can identify, based from one object, you can identify the other. So at this point, we realize that, okay, pairwise relationship can also help us to recognize certain types of objects. Then we extend the feature matching method and using the pairwise relationship as well. Here we have 3 types of objects we want to identify. For example, E1, E2, E3, and then 3 by 3 you have 9 possible combinations, and we have 3 pairwise features that we are interested in for object classification. For example, parallel. For example, smaller than, higher than, perpendicular, etc., etc. And then we ask the engineer, or in this case, a bridge engineer, to fill this number. Saying 1 means yes, always has. -1 means never had. 0 means sometimes yes, sometimes not, not always, which is ambiguous. And then we have the model. For example, in this simple example is we have 5 objects in a 3D model, 5 3D solid objects. 5 objects. We have 5 by 4 is 20 possible combinations because it won't check the combination of itself. So then the computer also generates this feature matrix, and the same process. We calculate the inner product, calculate the similarity value, and then from here the highlighted cells shows you that all these cells shows you the value that object 1 is element 1. This object is this type of object. Object 1 is element 1. So that's, if you say we have m object in a 3D CAD model, we have n types of objects we want to classify. So then you have 2n multiply m minus 1 cells shows you this object is this type of object. So for example, in this case, object 1 is element 1. The similarity is calculated by 1 add 3 and add -3 add etc., etc., all the value in these cells, and then divided by 2 multiply 3 multiply 5 minus 1. So this gives you the similarity value, that how similar O1 is E1. Similar way that you can calculate how similar L1 is E2 or E3, but the value just from different cells. So this is the example again that we have these 8 types of bridge elements. We have 59 objects in the model, and we calculate all the pairwise relationship, the value, and then we compile them. We calculate the inner product, and give the similarity value between relationship, then we use the sum. We sum them to calculate the similarity between object and object type. Then you just sort them to find the first candidate which are most similar to this object. So this is an example that we just manually prepare this bridge model. We use various objects to model these elements. For example, in this case, these objects, the share key was modeled as a FC column. We use column to model share key. And then you just click it, run our algorithm. It shows you, oh, this object is more similar to a share key than than column. So it gives you the matching gives you how similar they are, instead of just tell you this is the object. So this is one way to help us to classify the object based on this algorithm. And we have some larger scale example that we scan the bridge, we create a 3D model from the bridges, and we run our algorithm. And for object 1, it shows you the similarity value is 0.23, which means this object is more likely to be a good than a share key, than a tapping beam. If we choose all the objects using the first candidate to classify this object, we get 100% accuracy. So all the 331 objects in this model are all correctly identified. So this is the result. And also we did some comparison. Since we have a little bit of time, and then we can check a little bit about how we compare this model and this method with the previous one. There are also some rule-based method. Yesterday, Aaron, Math told us some first-order logic for the extension of ontology. Here, if you use this rule-based method, you can also define, for example, if object is horizontal, if it's also longitudinal, then this is a beam. If you can follow this kind of forward chain method to also identify this object, but you should be very careful. If you use their method, you may come with this kind of problem. If A and B, then this object is X. If B and C, then this object is Y. If you compile these rules just based on intuition, then you may end with this kind of problem. If A, B, C are all satisfied, and then what it is? According to the first rule, it still gives you, this object is X. And according to the second rule, it says, this object is Y. And if this algorithm runs iteratively, then it goes endless loop. So this is something that we cannot use the first order logic for this kind of classification. There are also some other ways that we previously developed. For example, using some algorithm to uniquely identify usable rules. But the difference between this rule-based method and our feature matching method is we have the assumption that our knowledge for identifying object is using some kind of a fuzzy logic. We have a boundary. Human, we cannot just use these kind of rules to clearly identify all the rules, clearly prepare all the rules, because sometimes the rules may not be validated for identifying specific type of objects. And yeah, I think that's it. Any questions?
Okay. Are there any questions? We have about 1 minute, please.
What's the primary purpose